Chemistry. This is our final lesson in the intermolecular forces unit. It's on heating curves. So heating curves show the temperature increase or decrease associated with heat added or subtracted for a substance. The curve below is for water at 1 atmosphere, which is just normal air pressure. So you see it in 5 different sections. You see 3 upward sloping lines and 2 flat lines. The first upward sloping line, what we're going to do is we're going to go from roughly 30 degrees below zero, below freezing, so that's ice, and we're dealing with water here. And we're going to go all the way up to right around 130, 140 degrees. And we're going to see how heat added to water affects the temperature and the phase of the water. So the first upward sloping line you see in the bottom left is increasing the ice from a temperature of negative 30 degrees up to 0 degrees. So during that period, when it's in between negative 30 and 0, it remains as ice. It's not melting at all at that point. Next, we see the first flat line at 0 degrees. And that is when the ice is melting. So while ice is melting, it remains at 0 degrees. It does not go up or down in temperature at that point. Once the ice is completely melted, then as you add heat, the temperature continues to go up. At that point, it's between 0 and 100 degrees. It's in the phase of liquid water. Then we reach 100 degrees centigrade, the water begins to boil and it begins to vaporize away. During that time, the water remains at 100 degrees. So remember, temperature is the average kinetic energy of the molecules. Any molecule that exceeds 100 degrees is going to float away as water vapor or steam. So the water that's still in the pan, in the state of water, in the phase of water, is going to still be liquid. So liquid water cannot be above 100 degrees. Once it goes above 100, it becomes steam. And then finally, the final upward sloping line is above 100 degrees. That is where water is steam, and it can increase its temperature at that point up to some very high temperatures. In this case, we're just saying about 130 to 140 degrees. So at points A, C, and E, to compute the heat required to increase the temperature of a single state of matter, so A is ice, C is liquid water, and E is steam or vapor, we use a specific heat equation. Now, you haven't been introduced to this equation before, but you will when we get into thermochemistry in the next unit. So here are the abbreviations over to the side here. Q is the abbreviation for heat. M is the mass of the water, so it has to be in grams. Mass of water has to be in grams. C is a characteristic called specific heat. It's how much temperature change occurs when you add or subtract heat from a substance. And it is specific not only to a substance, but to a phase. So water has different specific heats when it's in the form of ice, in the form of liquid water, or in the form of steam. So that's called specific heat. We'll talk about that more in the next unit. And delta T, that triangle is the Greek letter delta, means change in. Anywhere you see that in math or science, that means a change in. So it's the change in temperature. Point B is where the ice is melting into water, or it could also be, if we're going in the other direction, be where water is freezing to ice. So to compute the heat energy required for a phase change from solid ice to liquid water, we use what's called the heat of fusion. And that is represented by a delta H, and H is another term for heat. The difference between Q and H are technical at this point. Just remember that both Q and H mean heat. So it's called the heat of fusion. And you multiply that not by the mass, as you did with the specific heat formula, you multiply that by the number of moles. So the heat of fusion, again, is specific to a substance, and for water, the heat of fusion is 6.02 kilojoules per mole. So what that means is if you have 1 mole of water, that's 6.022 times 10 to the 23rd water molecules, and you want to melt, you have that much ice, I should say, and you want to melt it, you have to add 6.02 kilojoules, that's 6,020 kilojoules. If you want to go in the other direction, you have 1 mole of water and you want to freeze it into ice, you have to take heat out of it. And you would have to take 6.02 kilojoules of heat out of 1 mole of water in order to cause it to go from liquid water to ice, that is to freeze. Now there's a similar constant up there at point D, and to compute the heat energy required for the phase change from liquid water to water vapor, we use the heat of vaporization, and the equation looks identical. Q equals number of moles, but in this case you use the constant called the heat of vaporization, and for water it's 40.67 kilojoules per mole. So if you want to boil 1 mole of water away from liquid into steam, into vapor, you have to add 40.67 kilojoules. You'll notice how much larger that number is than the heat of fusion, and that is because to make ice melt, it doesn't take that much energy to do it, but to make water molecules actually break apart and float off into the atmosphere, it takes a lot more heat to do that. Okay, so now we're going to do an example. So compute the heat in kilojoules to heat 1 mole of ice at negative 25 degrees and make it go from negative 25 degrees centigrade up to 125 degrees centigrade. So we're going to go through all 5 of these steps to do that. And this, by the way, is the first problem on your assignment. So you can do your assignment as you're watching this. We did that in class. Okay, so here we go. Step 1, we're heating the ice from negative 25 degrees centigrade up to 0 degrees, so it remains as ice during that time. And the specific heat of ice, of water in the form of solid ice, is 2.3 joules per gram Kelvin. So what does that mean, that unit of measure? It means if you want to raise 1 gram of ice by 1 degree Kelvin, you have to add 2.03 joules. Okay, so here's the formula. Q equals mc delta T. So we have to go from, we're given moles. We're given 1 mole of water, so we have to convert that into a number of grams. And using the molar mass for water, 1 mole of water is 18.02 grams per mole, so it's 18.02 grams. So we have 1 mole times 18.02 grams per mole. Now we multiply by C, the specific heat for ice, and then the temperature change is positive 25 degrees. Now remember, a degree on the Kelvin scale is the same as a degree on the centigrade scale. They're the same thing. It's the same amount of temperature change. So it's 25 degrees whether it's Kelvin or centigrade. And when you multiply all of that out, notice everything has to be in joules because the specific heat of ice is in joules, 2.03 joules per gram Kelvin. So we multiply that, we get 914 joules, but generally in thermochemistry and the chemistry dealing with heat in chemical reactions or physical reactions, we convert to kilojoules. So you divide by 1,000, you get 0.91 kilojoules. And what we're going to do is we're going to tote this up here, and you look at the upper right, there's 0.91 kilojoules. Every time we do a calculation, we're going to add the number in because we're interested in the total amount of heat we have to add to make the ice go from negative 25 all the way up to steam at 125. Okay, now we're ready for point B, and that's the ice is melting into liquid water. The heat of fusion for ice to water or water to ice in either direction is 6.01 kilojoules per mole. So we have 1 mole, so it's going to be 6.01 kilojoules. Now, if you're going in the other direction and freezing water into ice, you would take out that amount of heat energy, 6.01. Since we're melting the ice into water, we're putting in 6.01 kilojoules of heat. So moles is 1 mole. The heat of fusion is right there in red. That's a constant for water. And so you get 6.01 kilojoules. And so we're going to add that up above. You see in the upper right, 0.91 plus 6.01 kilojoules. Okay, now we're going to move on to step C. Again, we're going to go back to the specific heat equation, and we see a 100-degree difference. So to go from freezing point of water to the boiling point of water in centigrade, it's 0 to 100, and in Kelvin, it's 273 to 373. The reason I'm using Kelvin is to show you that it is the same. It doesn't matter whether you use centigrade or Kelvin. It's 100 degrees on either scale. Specific heat of water, again, you can look this up on Google or look it up in a book, in a chemistry book, is 4.18 joules per gram Kelvin. So what that means, again, is to raise 1 gram of water by 1 degree Kelvin will take 4.18 joules of energy. So again, we got to convert the mole into grams, so it's 1 times 18.02 times the specific heat, and the change in temperature, delta T in this case, is 100 Kelvin. So that gives us 7,520 joules, or divide by 1,000, you get 7.52 kilojoules. So there you see it added up there in the upper right hand corner of the slide. Now we're moving on to point D. This is where the water is boiling into steam, and we use the heat of vaporization, which is 40.67 kilojoules per mole. And there we have 1 mole times that number, and that's going to give us 40.67 kilojoules to boil away our 1 mole of water. And so we add that to the running total that we have in the upper right. Now we move on to our final step. So now raising the temperature from 100 degrees centigrade up to 125, or from 373 up to 398, that's going to be a 25-degree increase. So you use the specific heat of vaporization, which is 1.84 joules per gram Kelvin. Again, that means that for every gram of water you want to raise by 1 degree Kelvin, it's going to require 1.84 joules of energy. And so you see the same formula down there as it's been written before, and it's 25 degrees that we want to raise it, so it's 830 joules, or 0.830 kilojoules. So now we add that to our total, and now we're ready to total all of the heat energy that we put in, and that turns out to be 56 kilojoules of heat energy. So know how to interpret this. The total enthalpy change, and I haven't introduced you to that word, you will be in the next unit. It again means heat. Enthalpy is a chemistry word for heat. The total enthalpy change required to heat 1 mole of water from negative 25 degrees centigrade to 125 degrees centigrade is delta H equals 56 kilojoules. Now, 2 other quick topics and definitions here. Viscosity is the resistance of a liquid to flow. Pancake syrup is more viscous than water. So what that means is that the sugar molecules in pancake syrup have a greater intermolecular force to each other. So while they are a liquid, they are stickier liquid, and so they don't move around each other quite as quickly. They're kind of like halfway between water and a solid. You could think of it like that, as a more viscous liquid. Finally, surface tension. So surface tension exists in liquid molecules because the molecules on the surface of the water are pulled only inward toward the interior of the water and toward other surface molecules. Molecules in the interior of the water are pulled in all directions and therefore do not exhibit this tension. So if you look at the molecule in the middle, you see the arrows pointing in all direction, and what that symbol is sigma force. It means the sum of all the forces is 0. You may have learned how to do force vectors in physics, and since they're all equal and opposite of each other, they end up zeroing out. So you don't have any tension on a water molecule that's in the middle of the water. But if you look at the water molecule on the top, you see arrows pointing to both sides. They cancel each other out. But the ones down below that are pointing downward, they actually pull the water molecule downward. So it causes kind of almost like a surface, almost like you had a plastic layer on top of the water. There's just a little more tension, a little more cohesiveness, and a stronger intermolecular force between water molecules on the top of water and water molecules that are down inside the water. Okay, and there you see a water bug over there. You see how it's standing on the water. You notice that its legs although they're pointed at the end, it doesn't stand on the points of the legs. It kind of bends the legs so that they are covering a greater amount of water area in the water, and that allows it to effectively float on the water. And you can see how it's creating these little indentations in the water. And it's kind of reminiscent of this guy, which is standing on water. And if that, whatever that little creature is, if it had curved legs like that, and it was light enough, of course, it could stand on water. It could stand on the surface tension of water. So that's kind of a little cartoon version of the water bug. Okay, that takes care of this lesson, and that takes care of the unit on intermolecular forces.